So this is the second part of the talk. I will tell you very, very little about computation, which is what you are mainly interested in. So just relax. Remember the old days of quantum mechanics in college, or the bad days of quantum mechanics in college, depending on your experience with physics. And just listen along as I try to tell you why I'm excited about joining the OpenAtom project and trying to put new capabilities in terms of physics and chemistry into it, and why we chose specific things to do it, and what are a little bit involved in, what are the difficulties we're going to face that we already know about, okay? So this is a new person joining this family. All right, Glenn pointed out that there's a thing called density functional theory. This is a Schrödinger equation. You may have seen it at some point in your life. If you haven't, it's okay. It describes electrons, those are these psi things, they're wave functions, which have energies epsilon, moving in a potential, those are the V things, okay? This is how density functional theory describes matter. There's some potential, like there's wells around the nuclei, so the electrons go there, and they make bonds between them, and it's described by a single potential. And so you solve this thing, and you have to do it self-consistently, and for large systems, it's very challenging. That's why OpenAtom took a while to develop, okay? But in the end, this is what you're doing. And then you can get many things out of this. And you have to make some approximations. So this potential here, nobody knows what it is, so you approximate it. But the structure is like this. So you've done all this work, and now you have these energies. Each electron gets labeled with an energy in this theory. So it's very tempting to say, well, geez, I'm all set. I've got the energies of my electrons, so I can use this to start calculating the properties of electrons when they change their energies. So what do I mean by that? Like you shine light on a material, and the electron will absorb the light and change its energy. That's important, right? I mean, we see stuff, photovoltaics, sun's energy, right? It's important. The electron is the thing that absorbs the energy. Or if you're making a current flow, the electron has to change its state. So it's very tempting to use this from DFT, and people have been doing it for a while, but there's some problems. So one problem is, let's say you have a material. What is the minimum energy you need to add an electron or remove an electron? That will determine some basic facts about the material. Here are three insulating materials, diamond, silicon, and lithium chloride. This is the actual number for the energy required in units called electron volts, the unit of energy, okay? For materials, the numbers in electron volts are of order 1. That's why the unit is used. Okay, not 10 to the minus 29 joules or something like this. Okay, so 1 eV, 2 eV, that's why we use these units. So these are numbers are looking like 1, 2, and 5 or something like that. These are the actual numbers, and this is what a typical DFT calculation gives you. You'd say, well, I don't know, they're positive, that's good. They're off by about a factor of 2 or something like that. Okay, does it matter? It actually does. So let's say you go ahead and use this kind of theory to calculate the absorption spectrum of silicon. Like, as a function of the light frequency, again in electron volts, this is a mathematical thing called the dielectric function, but it's just optical absorption. The black curve is real silicon, so it absorbs starting at 3.5 degrees. And the blue one is what this theory predicts. So first of all, it predicts it at lower energy, and second of all, the shape of the absorption is different versus frequency. You might say, oh, okay, 2 or 3. Here's a solar spectrum, okay? The bulk of the solar energy is between a half and around 2 EVs. Red starts around 2. So if you've never seen silicon and were a theorist doing ab initio predictions with electronic structure, you'd say, wow, silicon's going to be the best thing ever for solar, but you know, you're way off, right? It actually starts absorbing strongly around 3 EVs, which is already in the tail. So that's why it matters to get these numbers quantitatively. Okay? The typical quantitative accuracy you need is about 0.1 electron volts to be believable for an experimentalist to bother talking to you, to spend the effort to fabricate the material. And this theory is too poor. The reason it's poor is because it's a ground state theory. Its job is to describe the ground state of electrons, not when you're excited. So I will now tell you theories that came from the sky. I'll tell you a little bit in the next few slides what they're about. But just for now, the fix is here, okay? There's this thing called the GW approximation, and it gives you these numbers, which are not perfect, but good enough. Okay, and nobody actually knows how to go beyond GW systematically. So this is what we have. And then you can combine that with something else called the beta saltpeter, or BSE, which gives you the red curve. okay, for the optical absorption. Not perfect, but good enough, okay? And this is silicon. Here's another material that's familiar to you, glass, silicon dioxide. The colors don't agree, okay? So the red thing is your silly theory, the black thing is the experiment, and the blue thing is the beta saltpeter, okay? It's a very exciting theory for these classes of materials because it has good enough quantitative accuracy. Sometimes it fails, but usually a few tenths of an electron volts. So now we can make materials predictions that we believe. So you'd say, so why is this man here? And I'll tell you why I'm here in a few slides. Okay, so what is this GW and beta saltpeter that we would like to import into OpenAtom? More about it. It's all about exciting electrons, which is where the DFT is failing. So let's say you add an electron to a material. So here all the other filled levels, these little dashes are energy levels, and you put 2 electrons in the energy levels, and you run out and fill up the next level, basic chemistry. So when you add an electron, you got to put it somewhere empty. So these are the empty levels. So in DFT, you just look at the energy where you're adding the electron and say, that's the energy. But there's a problem. Electrons are charged. So when you add this thing, the other guys dynamically respond. Right? They move out of the way, for example. They repel each other. And then that changes the energy of this electron. Okay, so that's one thing that DFT misses, and you have to account for it. And another thing is, so far this is just, well, this pointer. Okay. How is it that optical absorption works? Well, you shine a light, and then you pump an electron from where it used to be to where it is now. So let's describe this a little bit more clearly. Light comes, that's the green thing, and then you move an electron up here. However, you leave a hole there, right? The missing electron. The missing electron is like a positive charge. Okay? So actually, the picture drawn here is kind of wrong, because I shouldn't be able to draw a picture where I just talk about the electron and the missing electron independently. I mean, they interact with each other. So somehow they correlate, right? And to give you a picture of what this means, let's say this is a material, and you absorb light to create an electron and a hole. They actually like to be close together because they attract each other. So think of like a hydrogen atom. The electron isn't on this side of the room and the proton over there. They're together. And then the collective object, say, moves around the room. That's how you should think about photoexcitation in materials. These are called excitons, in case you've heard the word. Okay? Excitons in something like silicon are not very important, but in all polymers and wider bandgap material, they're extremely important because that's what the light turns into. So when chemists talk about excitons are moving around and diffusing to an interface, I'm going to harvest the energy. We're talking about electrons and holes that were created by light, and they're sort of stuck together as a package. They move around, and you want to split them apart. But just to describe this, you need this beta saltpeter theory because these guys like to be next to each other, and that changes the physics. Give you a feeling. It's very materials dependent. Something like indium phosphide, this is 200 angstroms, which is 100 bond lengths. Well, that's huge, right? And silicon is 64 angstroms, and in glass it's 4 angstroms, like a bond length and a half. Okay, so different materials have different properties. We could, of course, do fudge factors for each material and get it perfect, but we have no predictive power. So we need a theory that can predict all of this. And that's the point of doing this beta saltpeter. Okay, so the point is, when you do optical excitation, these guys interact, and that changes the excitation energies and the absorptions. All right, so physical applications of these things are for photovoltaics, equivalently photochemistry, where light is absorbed and turned into chemical energy, or even ordinary chemistry involving transfer of electrons, because electrons will change their energy states. No light necessary. These are all problems where you have to deal with excited electrons. All right, so the GW's job is to talk about each individual electron at a time, including the response of the others, and this beta saltpeter is about dealing with their interactions. This is the end of the physics lesson. So now we're going to talk a little bit about practical matters of computation. Here's a system I calculated in the last few years for a photovoltaics project. It's got a nanowire of zinc oxide and a polymer that absorbs the light, one of these new proposed photovoltaic systems. There's something interesting happening at this interface. But I can only do this with DFT. Because if I wanted to use existing GW beta saltpeter codes, it would literally take forever. That means it would use up all my supercomputing allocation time for that calculation once. I couldn't test convergence. Okay? So that's so I didn't do that, right? Right. There you go. Thank you very much. Okay. At least we're not all mathematicians or something in this room. Okay. So then you go to paper and pen and you say, what are the scaling of these things? And in terms of the number of atoms, DFT scales like n cubed, like Len said, GW like n to the fourth, and the beta saltpeter like n to the sixth. Polynomials with powers. But this is very, very unrepresentative of the real world. Because when you run something that you can run, let's say GW and beta saltpeter, say 75 atoms of an insulator, here's how long it takes. If the DFT takes you 1 hour, CPU hours, the GW takes you 91, and the beta saltpeter takes you 2, even though the scaling powers are written there formally. Okay, so prefactors matter. And so we're going to be pragmatic in the OpenAtom project and first implement GW. And when we're happy with that, and we've got it down to from 91 to 5 or 4 or 3, then we'll worry about the beta saltpeter. So that's the plan. So what is this GW thing? This is the equation that I will show you today. You don't need to understand things in the equation. You just need to understand the structure of the equation. But since we're intellectually curious, let's talk about what this says. So this is all about the response of electrons to other electrons. So what does that mean physically? It means I put an electron here. It creates a potential, say repulsive, and that changes the electron density somewhere else. And I'd like to capture this process. So what is the change of electron density at position R when you change the potential at R prime? For every R and R prime in your simulation cell, you need this number, this matrix, so it's a matrix. So indexed with 2 positions in your cell. And to calculate it, this is the traditional formula everyone uses today, almost everyone. It's a double sum over all the states that had electrons and all the states that don't have electrons. You multiply their wave functions in this crazy combination and divide by the energy difference. And in principle, the sum goes to infinity, but truncated somewhere. So it's a double sum of an outer product. Because at R you have Ij, and at R prime you have Ij. So this is a very, very large outer product. And computing essentially a big matrix. Okay? So how is this going to be done in a plane wave basis? First you have to do a huge number of FFTs. In the plane wave method for the ground state, you only FFT the states with electrons in them. But here you have to FFT all the ones that don't have electrons too, in a pairwise manner, the J index. So we have a giant number of FFTs to do. Then we have to do a big outer product to accumulate this matrix. And the R grid is rather dense, not terribly dense, but pretty dense. And so this thing is giant in memory. And separately, the sum over J is very, very large. This is why it takes, quote unquote, forever. Right. So, number 1 and 2, lots of FFTs and giant outer product. In principle, if we had efficient parallel FFTs and really good linear algebra approaches, that would help us a lot. And these things do exist to some extent, although more work is necessary. Parallel FFTs. In step 3, we talk to people who are experts in computer science. How do I parallelize this thing right? Or in a way that scales well in things that I learn from them. And the part where I can do stuff as a physicist is in, say, changing an explicit sum into an implicit sum using, say, implicit inversion, which is lots of matrix multiplied by vectors. So this is something this is the kind of applied mathematics. Rather than computing a matrix, you would solve by solving an inverse equation. Okay? So there's some algorithms. There's some ideas about how to parallelize that I need to learn, and we all need to figure out. And then there's just figuring out how to effectively do things that are well done on paper, and we have to integrate them into this calculation. All right. So in summary, the method that I sort of gave you a caricature of is very promising, and that's why we're excited. We'd love to implement this thing in a way that doesn't take forever. It's very, very expensive, both in terms of computation and memory. And the plan is to try to implement this into OpenAtom. This is software that is right now a ground state code, and we have funding, me, Glenn, and Sanjay here, this grant to work on this as well as improving OpenAtom. So just to summarize, 2 sets of challenges. One is how to best parallelize existing algorithms. It's actually not trivial. Right? And we're going to rely on Charm++ to hopefully deliver the high performance. I have all reasons to expect. Okay, but from my point of view, performance is one thing. But the thing that really bothered me and kept me away from coding for 10 years was that every 3 years the computers would change. You know, like now is the bandwidth is this and the memory is that. Oh, there's GPUs. Everyone gets tired of changing physicist-written codes. You know how physicists write codes, right? They just write a loop, and then they sort of think a little bit down the line, like, ooh, I have MPI, so they split the thing up into pieces. And then it's like, but if the number of cores is more than the number of indices, what am I going to do? I'll worry about it later. Oh, no, let's transpose the, you know how it is, okay? Maintaining that kind of code is both boring, intellectually unrewarding, and fundamentally flawed in terms of parallelization, right? I don't want to be in that business. So this is why I'm here, because I think something like Charm++ or Charm++, if we can write a code and collaborate with computer scientists, deal with all those things that we do not have the expertise, the knowledge, or the training to do properly, hopefully we'll all gain. Okay? And then migration should be easier for the user. Of course, there's the issue of whether Charm will deliver on a new kind of a platform, but again, that's sort of not my problem, although I'm happy to help. Right? And then on my side, I need to think of ways of better using the compute cycles, right? Like better algorithms. This is something else. If you're interested, come talk to me offline. This is the job of a theoretical physicist or chemist like me and Glenn. And so hopefully in the next year or 2 or 3, we'll first implement a standard GW code to the algorithms node. The question is how to distribute it. And in the meantime, we'll work on new algorithms that will then be implemented, say, in version 2 of the GW. Thank you very much.
So in what way is this different? Is this different or similar than say, implementations of GW and VASP or quantum espresso?
Okay, so there are a few different kinds of implementations of, say, GW. There are proprietary ones that are already highly parallelized, but I don't know, one have to become friends with other people to get their codes. Okay, the public ones, for example, in VASP or in Quantum Espresso, are like the codes that I would write. There's been a great effort in parallelizing them, but fundamentally they're not built to be scaled where the number of processors exceeds, say, the number of electrons or some index in the loop. Fundamentally, they're not. If they have to be, then they do it like transpose and cut it the other way, and then there's this giant communication. But it's physicist parallelization. It's not the thinking of Charm++, which is, no, let's really cut this thing into millions of little pieces. Okay? And I just write a little codelet, and the runtime distributes it for me. It's a bit of effort to write it the first time, but then you don't have to ever write it again and worry about what crazy network architecture somebody came up with. From my point of view, of course, I do care that it performs well, but I have no expertise, and I have some interest, but I don't spend my life doing that. I'd rather do the science that enables me to do.
I first only want to add that this is an exciting new project, very generous grant from NSF. We have high expectations from it. Next year, expect some good results that we'll be showing with this. This year, we are starting. We have gotten some initial results and speed up and getting people in place and code in place and so on. But next year, we should have much strong results to show. Yep. I think there was a question that I wanted to ask, but I've forgotten by now.
So we just hired postdocs on the theory side, Glenn and I. They're coming in July, so definitely no results yet.
Not all of us are afraid of equations.
Okay.
Can you go back to your GW equation form, which is P? Yeah, there we go. In what sense is something here being a matrix inversion? So
okay.
You've been advised, stop doing, use iterative methods. So what would be iterated here?
Okay. So this is a good question because what's written here does not at all explain what's written here. So basically,
what are you solving for?
Okay.
What do you have?
Let's look at this. One way to compute P is to compute with this formula, right? The other way to compute P is to compute the columns of P by its action on vectors, right? These are equivalent things, but computationally they're very different, right? Because as you said, to compute the action of a matrix on a vector, you can do it iteratively. So the iterative method will allow you not to do this giant sum J, because if you can see, this is the eigenvalue in the denominator, so the J, J, and the epsilon, this is an inverse matrix of the matrix that gave you epsilon. So by iterative inversion, we should be able to either completely get rid of this sum or mostly get rid of this sum. Just an algorithmic thing. Exactly how to do it, because you don't know the eigenvalues, you have the matrix, it's expensive to apply it, you want to approximate it in some way. There's all these practical issues that we worry about. But does that answer your question?
Yeah, I'm a lot closer.
So with this project, we come full circle. We get this project running. We have a GWBSC. We can study excited electrons. We can study the material you talked about, and so we can design the exascale computers and beyond. So you actually buy your own cycles that way.
All right.
Okay. So let's thank again our speakers.